Very good morning. So today we have an in-house symposium regarding the event of Scicaffe, and there are many students who have come from Howrah Government School and College, and Howrah Government College, and they are mostly chemistry graduates, and they have largely interest in chemistry. So we thought that when we start the program, we have three lectures for you. So the first lecture is by our director, Prof. Maiti, who is also a very distinguished experimentalist of this country. He had one of the most profound experimental work of this country has done, and he works in the interface of chemistry, physics, materials. And so in between his talk and maybe after your talk, if you have some questions, you can always ask him regarding and get clarifications from him. And we have the second lecture by Prof. Tapan, who is a very distinguished coordination and organometal chemist and bioinorganic chemist. And he will give you a tutorial lecture on coordination chemistry. And the third lecture is by Dr. Prashant Chandra Singh, who will give you some lectures on spectroscopy. We are also very glad to have Professor Ghosh, a very distinguished quantum chemist and theoretical chemist of this country, and she is also from Howrah. So she has come from this and to encourage you, and she wanted to interact with you, and also let us know that Professor Ghosh, you might have also seen on TV. She is also one of the Scicaffe, and he was here. So you should be very proud that we have, and she decided to take her time out to motivate you, and she is also a very distinguished quantum chemist. So with this very small introduction, and of course Professor Maiti doesn't need an introduction, at least in an institute which he is heading. So with this small kind of a prelude, I would like to request Professor Maiti to come and share his thoughts and views, and like to talk to us about this. Thank you.
Good morning. Welcome all of you to Indian Association for the Reservation of Science, IACS, and thanks. Anand, he is also a very distinguished scientist, very well known in the country, and his team, Swastik and many others who have really helped continue this outreach program under the banner of Scicaffe, Science Will Come. So. And I'm extremely happy that you have come here to visit IACS, and I hope you have a great time here. English is okay, na? I think it's okay. So I may try to, but since I'm used to in English, so I think I'll continue that way. But if you have any difficulty, you can ask or stop me anytime. So I am given a topic like when and how and what next. Okay. So IACS is a very unique institution. We are also passing through a very important time because now this is the 150th year of this institute. You know that India, of course, I hope you know that it's a very big country, but we were actually ruled by a very, very small country called England. Okay, so I mean, it's not that England has been ruling all over the world, although if you think of their size, population is much, much smaller. The reason is that most of these countries where they have ruled, they are always busy fighting with themselves without realizing their own strength. I mean, India particularly, you can take an example. We have such a huge population, huge capability. In terms of intellectual strength, there is no lack of intellect. So everybody is very, very, they can make a mark, but most of the time you will see that we actually fight amongst ourselves without really trying to promote ourselves as a country together. This is true in every institution also. Like if you are in a small institute, you see a lot of fighting without really thinking of taking the institute forward. That has been the case in the history also. Our founder, Dr. Mahendralal Sharkar, he realized that if we as a country to become self-reliant, like if we want to have a leadership, then one of the most important thing is that we have to train ourselves in the technology that has been developing all over the world. Okay. So around that time, Europe of course was doing well because most of the scientific revolution was happening in Europe. And of course America came up with time because most of the scientists they moved to the US. So Dr. Sharkar realized that we have to make our people strong so that we can find our space, find our strength, and become self-reliant so that way we can take the country ahead. You know, he also had to face a lot of hurdles during that period, and his dream was to facilitate our education system by training in science led by Indians, because you know that if we lead ourselves, we know what is our requirement and we can actually take us forward. Because whenever we leave ourselves under the leadership of someone else, they will try to promote their own vision, own benefits and so on. So that's the way the country, the institute was created in 1876. So he was thinking about this institute 1860s or so. He was a topper in Calcutta Medical College. You know, I mean, we talked about Dhanvantari. So he was kind of the Dhanvantari of that time. So if anybody fails in medical practices, then he was the last resort, right? So, but he faced many hurdles, and he realized that if you want to utilize scientific equipments, which were not so much available, but whatever was available, Indians were not allowed to touch them. Because Europeans and the British, they thought that Indians are not trained enough to handle these equipments and so on. So he started thinking of an organization or association to cultivate science. And he was supported by almost all the intellectual leaders of that time, you know, starting from Chandra, Prashant, Singh, so whoever you can name at that time. Bengal was, of course, you know, has always been the intellectual hub of the country, and most of the good things, as far as intellect is concerned, was happening in Bengal. Even now, also, we do have that leadership. Somehow, we have to find our own strength. Okay, so that is the thing. We have to. So that way, Dr. Sharkar. So Ishwar Chandra Vidyanagar, Keshav Sen, they were the trustee board member, and he established his institute in 1876 on 29 July. It was at 210 Bobazar Street. Then, of course, Ashutosh Mukhopadhyay, you know, he was one of the greatest mathematicians of the time. He became fellow of Royal Society Edinburgh at the age of 22, which is unimaginable now. So he is the one who first published a research paper in mathematics from India. So he was teaching here at IACS, and there are many others. I don't name all of them. So most of the people who were Father Lapo, Jagdish Chandra Bose, all the names that comes to your mind, they all were actually working at IACS to train people. You know, most of the service were honorary, so they were not actually getting any fellowship salary or anything from IACS. So they were employed somewhere else, but they were practicing science in IACS. So that gave a platform to culture science. Okay? So whenever you finish your job and evening you can meet. So that way, science with coffee is the right right platform for us to discuss science and do it in a free mind without any reservation. Okay? So, Dr. Sarkar, he was of course very keen to provide salary and so on, but he couldn't do because most of the time the expenses were coming from his medical practices. That time, the most reputed British doctor, they used to charge a visit of 16 rupees for each patient. Dr. Sarkar used to charge 32 rupees, double of that. But still, he was burdened with appointments. So he was such a big name at that time. And most of his earnings from medical practices were used for buying equipments from abroad. Many others, like all the big names that we talked about, they donated, like Chandra, and many people donated, and that way the institute was running. But salary was not, they were not able to pay salary. Then after this period, then C.V. Raman, so Dr. Sarkar passed away in 1904, C.V. Raman joined in 1907. So then a new era started in IACS. He also was employed somewhere in Calcutta University, Initially he was an accountant and then he joined Calcutta University. And he was practicing science in IACS. And of course he did a lot of experiments with migrations, scattering, and so on. And all of you know the discovery of Raman effect, which got us the only Nobel Prize in science. Okay? So he realized that whatever light that comes out of a material, it's not just simple reflection. Reflection, if you took some colored light, it reflects with the same color. But sometimes what happens is that if that is able to excite some vibrational modes or something, then the scattering can happen at a different time. Okay? So if we can find out how much energy was lost during this scattering process, we can actually find out which material it was scattering. So identifying. So that's the strength of Raman. Today, many of the equipment sensors that we built, humidity sensors or many other things, they are actually based on the principle of Raman scattering. So it's a big revolutionary kind of a discovery, which actually got Nobel Prize. It's a well-deserved. Of course, we have many other activities which happen in India, and they could have got Nobel Prize. But this one was a successful one. So he was here around till 1933, and then of course he left to IASC, so he became the first Indian director of IASC, Indian Institute of Science. And so he got Nobel Prize in 1930. 1928 is the discovery of Raman effect. National Science Day. It was celebrated in honor of the discovery of Raman effect. And 1930 he got Nobel Prize. Then the Krishnan period started. So K.S. Krishnan, who was a co-founder of the Raman effect, so he joined IACS, and that's the time, for the first time, IACS created a position which is a public, and it's called Mandala Sarkar Professorship. Okay, so that's the way the thing. Then we had a lot of activity on X-ray scattering, X-ray diffraction, So crystal structure determination, like if something is showing anisotropy. Anisotropy means that in every direction it doesn't show the same kind of a structure, okay, or same kind of a behavior. So these are many fundamental things that time was discovered. Around 1942, of course, he left, and then Meghnad Saha took up the leadership of this institute. Okay. So he became the president of the association, and he realized that this Beaubazar Street building is not really good enough to support the research activity that IACS should carry forward. So that way, then he of course approached Dr. Vidhan Rai, another legendary doctor, and so he donated land here, about 9-acre land in Jadavpur, and the institute was built. So the foundation stone was laid in 1948 by Dr. And the institute started functioning from around that time. So you can see that the first 75 years, almost about 75 years, we spent in Bhubajar Street. Okay? And this campus has become another 75 years old. Now it's time to take the step forward to create something new. Okay, so and of course now a lot of things happen in this campus. So, one of the important things when you enter, you could have seen that we have an exhibit on plasma enhanced chemical weapon evaluation system (PCV) setup, which was indigenously built in India to fabricate amorphous silicon solar cell. Solar cell is essentially built on silicon. Nowadays all the computing technology, digital technology, they are based on silicon. The chips are made on silicon. But crystalline silicon can be pretty expensive. So he thought that if we can use amorphous silicon and build solar cell, he came up with the technology. So it's a very novel technology was built, and it was translated to various companies like BHEL, Bharat Heavy Electricals Limited. So India also, the government of India funded under 8 5-year plan to have this kind of activity with solar cells and so on. Then many other companies, they took it up. So this is one of the first research, the first example of research translated into technology that happened at IACS. So it's a happening place. Of course, nowadays we don't have the solar cell based on because the crystalline silicon price has gone down significantly. China produces, they have found a resource and they started selling very cheap solar crystalline silicon. So amorphous silicon technology is there, but it's not being used. Okay? Now we are in the university, so we give our own degrees and many activities which are going on. So basically our aim is to do fundamental science whichever best way possible and see that if it can be exposed to the society, train people, and at the same time also if the translation is possible. So everything, and I think that in India IACS still leads in this kind of So there are many things I have listed here. I don't think I'll spend much time here because I have half an hour. So as you know that Manulal Sarkar, so soon after discovery of X-rays, X-ray was discovered by Rontgen, 1895. So Manulal Sarkar got the Rontgen tube and did X-ray imaging. Today, if your bone is broken or anything, you take X-ray. So the imaging was first done by Manulal Sarkar in 1896. Okay? So Ashutosh Mukhopadhyay, of course, as I said, that the person who published first paper, J.C. Bose, he is the inventor of wireless transmission. Today we are sending rockets reaching Moon and Mars and so on, all this. But all the control are happening sitting in India. This is because we are able to send signal through wireless kind of technology. And this was thought by some Indian 150 years back. You can see, the kind of mind that we have, rich mind that we have. Then of course, I want to take K.S. Krishnan, Shama Prasad Mukherjee, he also one of the greatest mind that Bengal produced and also contributed significantly in IACS as a trustee board member. Then, of course, Meghnad Saha, Saha ionization field. So, normally, the stars, they where the temperature is very high, because it emits light of all kinds and so on. So there, any material which is there, that will be in a plasma state, ionized state. It won't be normally like the material that you see now on Earth. So how that happens, the basic formula was given by Mendelssohn. Actually nowadays also whenever we do try to study stars, the reactions whatever is happening, cyanide is really used. It's one of the basic equations. So he should have got Nobel Prize of course, but unfortunately it was not recognized. Then S.N. Bose, he was here till his last, he passed away in 1974, so he was here. Bose statistics, it's one of the fundamental discovery, and half of the particles that we know all over in this universe, they are bosons. You have fermions and bosons. You know fermions, okay, like electrons, protons, neutrons, which has half integer spin, and photon, for example, phonon, they are bosons. Then Amol-Raychaudhuri equation was discovered at IACS. This is also one of the basic equations. Einstein's theory of general relativity. We all talk about relative motions. Relativity is one of the, when you think about spins, magnetism and so on, without relativistic treatment, you cannot really imagine that there is this things are there. So Einstein, of course, is the first one who proposed it, but he always used to think about the static universe. And Raychaudhuri, he thought about that the entire universe also is not really so static. It can have a different kind of motion, and he gave a basic equation. So, which helped us to find out what is the origin of this universe. We heard about black hole, supernova, and so on. So, if you want to reach there, earlier what was there, you have to use Raychaudhuri equation. Okay? So, it's just the general relativity is not enough. So that basic equation, which could have also got Nobel Prize, but not really. Then PECVD setup I told about Ashok Bodua, which was built, and the exhibit is here. There, I'm not getting into the details. Okay. So India, of course, has been recognized by various international bodies. I just want to tell you three things. One is this Institute of Electrical and Electronics Engineers, IEEE. It's an international body that recognizes what are the milestone discovery happened all over the world. And in India there are three. One is, of course, the discovery of Raman effect, which so IACS actually has a milestone on that. Then the other thing is, of course, JC Bose, this wireless transmission. So both these were recognized in 2012, 15th September. Okay? So if you go to Bose Institute, they have a nice archive and you find the thing. The third thing which has happened by Govind Swarup, he is from PIFR. So he built a very unique GMRT called giant meter wave radio telescope. आजकल मैंने तो अगर देखें निश्चय जे we talk of gravitational wave. नाम सुने निश्चय. Gravitational wave is essentially So detecting gravitational wave is really a Herculean task because the signal is so weak. Anything that you think of detecting it is very difficult because the noise that is available. Whenever you are doing experiments, it's one of the most important things that you need to remember. the things or the instruments or setup that you are using to detect, you must know what is the sensitivity of this. Okay. So I have heard many, I mean here also many people they visit. For example, somebody is talking about a very minute change. Right? And if you, for example, tomorrow weighing machine weighing machine has a digital display and you have certain number after decimal place. Okay? The instruments are built based on what is the accuracy that it can provide, okay, based on the number of decimal places are decided. Okay? So you can have a very sensitive balance. Chemistry rules always, I mean, you can have 4 decimal place and so on. So whenever you are using an equipment, you must know what is the sensitivity, how accurately you can decide. I mean, you can. So just by changing the display with a large number of digits after decimal doesn't help. You have to know the equipment is sensitive enough to detect that or not. Many people think that way. I mean, I don't want to bring up that question. But anyway, so this GMRT is another milestone that was actually that got recognition. Bengal actually had many such discoveries like ocean, X-ray scattering that we talk about. It was discovered here. Spontaneous nuclear fission. Nuclear fission, आजकल हमरा तो जानी nuclear bomb and so on. Nucleus also you can break. So originally, of course, people thought that it's unbreakable. Then people found that you can use neutrons to break nucleus because neutron doesn't have a charge. So you can bombard nucleus by neutron. Otto von Guericke Nobel Prize, got Nobel Prize for that nuclear fission. But soon after, in Calcutta, Samadas Chatterjee, I think, so he discovered spontaneous nuclear fission. Like there are some nucleus which can spontaneously break. You don't need neutrons. Unfortunately, that paper, didn't get published because people thought that you were dreaming and so on. But eventually, others got the credit. But what I'm saying is that many of the fundamental discoveries which has happened, and that was actually happening in Calcutta. Now, the last part that I want to say, what next? So here, before I say a few things, I wanted to know what you think we should do next. The science, of course, nowadays a lot of things are happening. Anybody wants to make a suggestion that what we should do? You may please raise your hand. Anything that you think, because এটা তো ডিসকাশন, তো আমরা সবাই একসঙ্গে বসে ভাবার চেষ্টা করছি যে what we should do.
তোমরা তো জেন জেড, তোমরাই তো সাজেশন দেবে।
Yes. You are supposed to be the leading leader for the future.
Sir, bolo. Give some suggestions, please.
Anything that you think that আমাদের এটা করা উচিত. It doesn't matter which subject it is. Okay? Whichever subject you think that আমাদের দেশে এখন প্রবলেম কি, কোন জিনিস আমাদের অ্যাড্রেস করা উচিত. You see, unless you suggest, you cannot blame us if we take a decision. Because you are not speaking up. Don't feel shy. Anything. There is no question which is stupid. Okay. The most stupid question actually leads you to the discovery.
I can help them.
Yeah.
Traffic topic, you must have faced. Very topic. You can help and say those things. Did you face it?
হ্যাঁ, তোমার কি কোশ্চেন?
বল।
To focus more on
Yes.
to focus more on AI/ML models.
Yeah, that is an important. But you are basically trying to say how others are talking. I mean, these are keywords that are used by everybody nowadays. See, quantum computing, AI, and all. Artificial intelligence is one of the most important, maybe most dangerous also. You don't know. I mean, maybe you have a video published which you have not even talked about.
Infinite videos.
Yeah. So.
deepfake videos.
Yeah. So there are so many things which are getting circulated. That is one thing. But apart from these keywords, you have anything that you think we should look into?
তোমাদের ক্যারিয়ার মানে বিএসসি পরে তোমরা কি করতে চাও বা সেখানে কি
To make a more sustainable approach to the environment, can we do some more work something?
তোমার নাম কি?
Sir, to make a more sustainable approach towards research and environment, can we like extend our work towards bioplastics? Are bioplastics equally useful as normal plastics, like that towards sustainable analysis? Can we
Yes, it's a good idea. And of course, তোমরা জানো নিশ্চয়ই যে a lot of people are actually working how to, one is that, I mean, how to take care of these plastics and also how can they be reused, because plastic is very difficult to make it biodegradable and so on.
and fuel efficiency,
Yes.
like we are having a bigger problem in our country, like E20 and all of petrol something. So towards something more sustainable and also like such that the engines of the car are not getting
বাংলায় বলতে পারো, please.
and then
Okay. Yeah. Thank you. Thanks a lot. Yeah.
Sir,
This. Yeah. Hold
sir,
on.
one more question I had. Sir, how can we approach towards PhD after our school?
You see, in IACS, of course, we have a very well-defined program. We have been now, of course, the host is there. So, there are two types of entries. One is where you can enter for the bachelor's program. If you have completed bachelor's, you can also enter for master's program. And if you have completed master's, you can also join here for PhD. So, all the three entries are possible. For bachelor's, you know that from which year onwards we are taking students through ISAR aptitude test. For masters, we are taking JAM, that IIT conducts. And for PhD, you have to apply. I think you can tell directly there are interviews. So, so there are possibilities as well. And if you are able to get a national fellowship like if you have here, so that helps significantly. But we do have our own fellowship program also.
Shall I answer?
Yeah.
Okay. So basically, we have admissions to PhD 2 times every year. Once for our, around April, May, we have the advertisement, and again another one October, November, we have the advertisement. So in that, we see that whoever is taking students, what requirements and all that, and depending on that. You can also write to any of the faculty members at IACS. We always try to reply as much as possible, and we can write. Thank you.
Any other questions? Career counseling?
Yes.
Please identify yourself. Tell which year.
AJ.
From Chemical Science, School of Chemical Science. I have questions that.
You are from our school.
Oh, I see. Go.
My question is from biochemical. As we know, also, that the CO2 is a waste product and byproduct. Can we use CO2 as an essential product in our future?
I think a lot of people they are putting an effort to utilize CO2 like for fuels and many other things. A lot of activities are going on. In IACS also there, if I know correctly, even this but here also there are a lot of people in chemical science.
There is also a very big group in PIF.
Yeah, of course, yeah.
Which wants to convert CO2 issue.
This effort is going on. I mean, it's a good thought, and people have been thinking about it for pretty long time. So, how to actually use CO2 to, you can create fuels or something else.
Because in future, the oxygen is very good.
Absolutely. Anything else? Okay. Okay, so maybe I can just tell you what we have. How much time?
Maybe, I mean,
Okay. So, just very briefly, I tell you what all things are happening. So many things which are happening, I don't really, I mean, we have colleagues, so you can ask them, you can visit labs and so on. But one of the things, for example, this solar cell, since I talked about solar cell, I thought I will talk about indoor photovoltaics. So if you have lights inside, which is already using the power, you can use this to energize your low power required like displays and so on. Okay, so which some activity going on. Then another thing that we often talk about, like this discovery of how to create drugs for DNA, it's a genetic disorder. So so you can find out a molecule how to create some expensive drugs in a cheaper way, or there are many drugs which are required and you don't know them, so you can try to find, like cancer related activity, a lot of things are happening here and so on. Okay, so now I want to give 2 slides on my personal expertise. Okay, here, I don't know if this video here is done. So you can see there is a black kind of object. You will find it in YouTube also available. So this one is a magnet. Okay. Now you can see that you could keep it on this and it was lying on that. So what they are doing, they put a liquid nitrogen. Now you see the magnet what it is. You see it's floating. It's a beautiful example which everybody knows, but it's a beautiful example of how material can behave, which you cannot imagine just by thinking about it. Okay? So because it has gone into a phase, you see, I mean, you can do anything, it just remains stable there, and it's just floating. So magnetic levitation that we talk about nowadays is based on that. So this is basically a superconductor in normal temperature. It's a normal material, not superconductor, so you can put a magnet on this. But if you cool down using liquid nitrogen, then it becomes superconducting, and you can see that you can lift it and put it on the side, and then it warms up, and it really comes to room temperature, and it loses its superconductivity, and the magnet forms. Okay. So this experiment you can do at home. I mean, whoever has liquid nitrogen, and if you can make YBCO, yttrium, barium, copper oxide, or visco, which are people are making that, which has a superconducting transition temperature just above liquid nitrogen temperature. So it becomes superconducting, and you can actually see that how the magnet behaves. Normally, do you have any idea what you mean by heat? You know what heat is? What is your understanding about it? Tomorrow question, what is heat? Have you thought about it? Sorry? No, that is not a question. Tell me what is heat? You know, if anybody can say anything about it.
it's a thermal radiation.
Huh?
Thermal radiation.
No, I'm asking what is this thermal, I mean, harm that you are talking about, what is this thermal radiation? What is it? You have any idea? Anybody? Actually, I mean, in the old days, if you want to heat it up, what you have to do? You have to light a burner or something. Nowadays, you can use a microwave oven to heat it up also. There is no burner or nothing. Okay, there is no temperature increase there, but still you can heat it up. To the best of my knowledge, and as far as I understand, nobody understands what it is. Okay? Actually, we have no idea what it is, but we know what it does. Okay? So it means that if you heat it up something, there are vibrational modes, something is vibrating, it gets excited, and so on. But normally you actually don't know something is hotter or cooler. Just by looking at it, you of course don't know, unless the color changes. Or, I mean, if you think very carefully, actually we have no idea what actually is happening. But vaguely you can say that if something is hotter, the atoms will vibrate more vigorously, isn't it? Now, if you cool it down, what will happen? The vibrations will die down, isn't it? If you go to absolute zero, what will happen? There will be no vibration. That's the thing that we can intentionally, I mean, if you will think. For electrons also, people are thinking that way, that if you cool down, normally what happens is, what is electric current? Electrons flows in a conductor, okay? So if you cool it down, what will happen? They will face less resistance because the atoms are vibrating less. But electrons' motion also should get affected now if you cool down. So some people thought that if you cool down to absolute zero, electrons will stop moving. Okay? There's something. So if it stops moving, resistance actually can be very, very high, in time. Or, I mean, it will saturate at some point. But when people actually did an experiment, so this person, Kamaldi, he found that actually the resistivity goes to zero. Means that electrons move without any resistance. It's like a fluid moving without any distortion. Superfluid. And of course, there are many Nobel Prizes gained. A lot of research is happening how to find a superconductor at room temperature. So far, nothing has happened. So the highest, we know that 1993 around 133 Kelvin. After that, many people, this is in ambient condition, like normal condition. Now, another example I'll try to give you. I'll just spend 2 more slides and then I'll stop. Okay. You have seen traffic. You have come when you are coming. Now, if we assume that the traffic rules are religiously followed, it means that if you have a one-way traffic rule, so the one which is going in one direction, they will continue that way. There is no break of norms. So that means that if a car moves in this direction, they will continue this way. If the car moves in this direction, they will continue in the other way. Okay? Immediately, you can see that you see the white light. The ones which are going in this direction, they will show you the red light. Okay? Now, for example, assume that there is some accident happening, some car broke down. What will happen? Nothing will happen. Because as long as you follow the norms, okay, that one-way traffic has to be followed, maybe there will be some clustering here, but the cars will continue in this direction. This also will move in this direction. Electrons also follow similar rules. Okay? If you have a material where electrons of a certain kind, say spin up, moves in one direction, and if you make the rule fixed, then only up will move in this direction, down will move in this direction. So then what happens is that whatever you do in the material, cool down or anything, make repairs, anything, this rule will not be broken because they are protected by something else. These are called topological materials. So I'm not getting into the details, but what happens is that if you plot energy as a function of momentum, this shows a linear dispersion. Okay, it looks like this. So these are called Dirac particles. So now you know Einstein's equation, jara jano. E square equal to P square C square plus M square C to the 4. Okay. Now you can see if E is proportional to P, to make that you need to make M0 0. Okay. Then E becomes proportional. So that means that if you want to get a linear dispersion, you need to have M0 equal to 0. M0 is the rest mass of an electron. That means the electrons which are following these norms, they are like massless particles. It's a very interesting concept. These materials exist. These materials, যেমন superconductor বললাম, topological materials, these are called quantum materials. আজকালকার দিনে a lot of people talk about quantum computation. Okay, you have heard about quantum computation, which is one of the key areas. Okay. So this quantum computation can be done very efficiently if you are able to discover a topological material which is superconductor. Okay. A lot of experiments are going on. So there are many things have happened. Anybody is interested, I can talk about it more. But a lot of research is going on in these days. So what IACS is doing in the future, I have shown you that we are working on medical science, like fundamental research which will support health, environment, okay, which will also support technology. Okay. So these are basically the ideas, and of course we are a university. So we are trying to expand our teaching program as best as possible. So now, after 75 years in this campus, we think that we should create another unique campus at Bahulpur. So this is called Prashant Center, IACS at Bahulpur. So in honor of this great visionary, Dr. Prashant. So this is basically a brief sketch. So if we succeed, after maybe a year or two, you will be able to see some things are there. So the institute will become bigger with science park where we can have provision of translating science to technology, which IACS has been doing well, as well as doing fundamental science. And of course, many of you, like college students and so on, will visit us and get exposed to science. Okay. Thank you very much for your attention. So, if you have any questions,
so I'm sure we will have some time for discussions, but before that, we would like to take a group photo with the young students. Please come along with the experts. Sir, experts.
They only undergraduate students who are visiting us. Madam, after
Thank you. So he is available by be contacted by email. You can write an email to him, and he will be here for a few minutes, and then he has to go for a second.
So, anything you want to ask now, or okay? So when will you contact them? Yes.
So after this mesmerizing lecture, we will have traditional chemistry lecture by Professor Tapan, who is also an expert of bioinorganic chemistry. and coordination chemistry. Professor Paine has been here for more than 15 years now, and he is a prolific teacher and prolific academician. He has graduated several students, and he is known as a kind of world expert in this field. So the audience is all yours, and I have listened to Professor Paine, and he is one of the wonderful teachers in coordination chemistry and inorganic chemistry. So Tapan, the stage is all yours, and he loves to demonstrate chemistry.
Thank you very much, Anand, and good afternoon, everybody, and welcome to IACS. Okay, Professor Doctor requested me to talk on this topic. This is a topic that I have not decided. So it was decided by Professor Doctor. But, let me talk about, as you have seen the wording of the title, the development of coordination chemistry. Just I'm not going to teach you what coordination chemistry is and what coordination chemistry can do and what is the different area that coordination chemistry is connected to. So before I get into it, you have seen the lecture given by our director, Professor Maiti, and he has touched upon the genesis of IACS and where we stand. But history is very, very important. But definitely we should live in history. We should always learn from history and take us to the next level. But knowing history is important. When we are in a classroom, I have given something, it's very, very important sentence that learning history is important. When we learn a topic in a classroom, or when we as teachers teach something in the classroom, we give a very dull way of giving some knowledge about theory, some topic, but we rarely get the opportunity because of the time constraint, what background a particular theory was developed, be it economic, social, geopolitical, and also the scientific background at that point of time. So when I'll just give you a background of this particular topic, that under what circumstances some revolutionary scientists eventually came up with this idea, and that has implications far-reaching. So, you all know that about 130 years ago, Rabindranath Tagore got Nobel Prize on literature. Professor Maiti was showing something also. In the same year, the Physics Nobel Prize was given for the work where the lowering the temperature, how resistance actually goes down, the electrical conductivity and resistance that he was showing. In the same year, the Chemistry Nobel Prize was given to a gentleman, his name was Alfred Werner. And he was given Nobel Prize. This is the first Nobel Prize given to an inorganic chemist. Earlier, all the Nobel Prize were given to organic chemists, and he was given the Nobel Prize in recognition of his work on the linkage of atoms in molecules. See, it's a very important topic. Linkage of atoms in molecules, and particularly the molecules that are completely different that were known and that opened up new field of research, especially in inorganic chemistry. We, the practicing inorganic chemists, whatever we do, everything we do because of this particular theory, and that's basically coordination theory. As I said, understanding of the life and work and also the background for the development of theory is very, very important to know that subject much deeper, which not only gives us a scientific background of that discovery, but also gives us a lot of information and provides, kind of inspiration. And that is the objective of this particular lecture, is to give you this inspiration that, see, if you can think out of the box, not going with the wind, can eventually lead you to discover something very different. Okay, so just to give you this one, a little bit of geography as well, because as I said, geopolitics is also an important thing in any discovery. So Alfred Warner was born in a small province here. It's called an Alsace province in France, and in a small town called Mulhouse. His father was a foundry foreman, mother was a housewife, and he did his primary education here in this small town in Mulhouse. And at the age of 18, because he was born in 1866, about 17, like all European countries, when you finish a school, it's not that you will go to college straight. You have to serve military. The purpose of serving military is to create discipline, so that as a citizen, you know that what is your responsibilities, and you should do things in a responsible way, in a more disciplined way, and this way you become a good citizen of a nation. But why I have shown you this map? This is important. If you know that today, because this is called the Rhine River, and Rhine River separates Germany, France, and Switzerland. And this part, which is shown in pink color, at that time when he was born, this part of France was occupied by Germany. And that eventually led to First World War. And because it was a German-occupied territory, when he passed school, he had to serve German military. So he was stationed during his military training. He was stationed in a town called Karlsruhe. I'll come into that, but as a student, he had a lot of interest in chemistry. He purchased chemistry textbooks, and he had so much of interest that at the age of 18, he wrote a paper. And he presented that to his professor, Professor Nolte, and he asked his professor that how long it took roughly to become a professor. At the age of 17, he was asking his professor how long it will take to become a professor. As you will see, note the year, it was 1885. And exactly what age he will become a professor. This is the last page of his paper that he presented to his professor. And this is the signature of an 18-year-old gentleman. As you can see, how smart, bold, and really a kind of a confident person that signature indicates. Anyway, so during his training, military training in Karlsruhe, which was actually adjacent to this military barrack where he was stationed, was adjacent to technical schools, what today is called Karlsruhe Institute of Technology. This is one of the big universities in southwest Germany. And there, after days of military training, he used to attend chemistry lectures in the evening at the Karlsruhe Institute of Technology. And he had the opportunity to listen lectures from Carl Engler. Many of you know he was an industrial chemist and who worked with Bayer. Bayer is a big chemical company, you know now today. And he was actually doing program or different research projects given by BASF. It's a big chemical company. And that time, it was kind of an industrial revolution period that was going on in Europe. Because the colonial powers, they realized that they would lose their colonies. So many of the raw materials that they used to import from these colonies, they realized that it is impossible to sustain it, therefore we need a synthetic way of getting it. One such, all of you know, is indigo. Because they used to import it from India. And this gentleman, Carl Engler, who was an expert on indigo, and he was working on indigo in collaboration with BASF. And they were trying to develop how to synthesize this, and he was the person who synthesized, not from natural sources, but in laboratory, he synthesized this chemical in collaboration with BASF. And here, color intrigued Alfred Warner. See, the color of this chemical was actually intrigues Alfred Warner. And that was the beginning of everything. So what he did after finishing his military training, he went to Zurich because that was a good place. He wanted to avoid German-occupied territory. So he wanted to go to a neutral place, Switzerland, and he went to Zurich. But since he did not study in high school, so what he had to do, he had to go to a technical school because he did not, so that he will not get a kind of a degree program. He was in a more like a technical education. So he's got admission in technical high school in Zurich, and he got a lot of great teachers there in industrial chemistry. And in 1889, after 3 years of undergraduate, he got a diploma in technical chemistry, not in degree in chemistry. Okay, now let us see what was happening that time, the second half of the 19th century. Organic chemistry was rapidly developing because of the utility of organic compounds in food sector, in agriculture, and many other sectors. And great discovery took place by the time that where the father of organic chemistry, Kekulé, who had shown that carbon can form 4 bonds. And in 1874, when he was a young school student, that time Van Hoff and Lebel shown that if you have 4 different groups at carbon, then that gives rise to optical activity, and they can show mirror image to each other, which are basically enantiomers to each other. So that was the organic chemistry, a lot of development was taking place. But interestingly, what Van Hoff and Lebel, you all know probably that what experiment Van Hoff and Lebel did, don't say hybridization, that's why it's tetrahedral. They did some experiment, and this impeccable experiment allowed him, or allowed Lebel and Van Hoff to come up with this conclusion that the geometry of the carbon will be tetrahedral, purely based on the knowledge of geometry and chemical intuition. And to him, to Alfred Warner, at that time he was thinking that is it a property of carbon, or it could be a property to other atoms also, but is the valency fixed like carbon for other elements? Because remember the time when electron was not discovered, when nothing was discovered about subatomic particles. Only how atoms combine with each other, that was their objective. So in about 1 year, he worked for 1 year and he submitted his PhD thesis on the spatial arrangement of atoms and nitrogen-containing compounds. What he has shown that if you have nitrogen, and if you have 3 different groups of nitrogen, because the fixed valency of nitrogen is 3, and then nitrogen would also show optical activity, but the problem is that they rapidly exchange, and therefore isolation of the 2 isomers, the enantiomers, are difficult due to umbrella inversion. And you all study those things in your first year undergraduate, and that was basically his PhD thesis. He also worked on the stereochemistry of nitrogen-containing compounds and came up with the idea that if you have oximes, that oximes can, like aldehyde and ketone-derived aldoximes and ketoximes, they give rise to cis and trans isomers. So he got PhD in 1890 with the spatial recognition of superior performance. And his PhD thesis, as I had said, that it was on the spatial arrangement of atoms in nitrogen-containing compounds. Completely switched from carbon, where everybody was working on carbon. He thought nitrogen-containing compounds are interesting and we should know what was happening at that time. So this is the first page of his first PhD paper, which was published in Bulletin of German Chemical Society in 1890. Why I have shown you this at the end of this, because it's written in German, at the end of this paper, because we write acknowledgement sections, right? That, okay, this person helped me, we got money from that source, and I discussed this work with him. These are the things that we always write in the acknowledgement section. In this paper, in the acknowledgement section, I just put it in English here, that his PhD supervisor, Arthur Hans, who was a great organic chemist, he wrote that the undersigned only fulfills his obligation to fairness by declaring that in the case that the results described above have important consequences of some kind, the theoretical framework published by himself and Mr. A. Warner is in all its decisive parts the intellectual property of Mr. Warner. So it's basically boss is saying that as a boss, I'm writing this paper along with him, but whatever is there, whatever intellectual component is there, it's basically Mr. Warner's, not mine. That indicates something, a genius that was working with him. So it's from this picture, although very difficult to understand who is a boss and who is a student, but this is a later picture. As you can see, Arthur Hans, one of the tall figure in organic chemistry, many of you know Hans synthesis of pyridine, pyrrole, Hans ester synthesis. These are organic textbooks at undergraduate level you all study. So this is basically Arthur Hans, his work. And this is Alfred Werner. They remained very good friends for the rest of their lives, but although they were very opposite characters. I'm not going into what were their characters because we are discussing science. What I would like to share what Tapan shared. Tapan is basically who wrote the biography on Alfred Werner on the 100th century of Alfred Werner in 1966. But Tapan shared that despite Hans's more than 500 publications, his greatest discovery was probably Alfred Werner. Okay, some other PhD publication on cis and trans isomerism of genes, so it's basically a geometrical isomerism, and also the stereochemistry of peripheral of genes and others, which were published in the same year in the Bulletin of German Chemical Society. Okay, what next? So, it was a time when a lot of things were happening in Europe. A lot of developments were taking place. And everybody was trying to train themselves with a changed scenario. That's essential, right? When things change, one has to really go to like AI, machine learning, we were discussing. We should not ignore that. We should adapt with the changed technology, changed way of whatever is happening around us. So his PhD supervisor, Arthur Hans, advised him that why don't you just learn a little bit of photochemistry and thermochemistry? Because nowadays a lot of industries are coming up. They need thermochemists. They need experts in thermodynamics. So he asked him that you go to Paris and then work with Marcelin Berthollet. He was a great another Nobel laureate in thermochemistry. Okay, but he did not like this place because the work he did not like, something was going on in his mind. So after 6 months, he returned back. He returned back in June, and then it took a few months, July, August, September, and October. 4 months he took, and then he wrote his habilitation thesis. So what is habilitation thesis? Just for the students, let me tell you that if you want to be a professor in German university, your PhD thesis is not enough. You have to write another thesis, and that generally takes 5 to 6 years. Another 5 to 6 years, then you are eligible. Doesn't mean that you will become a professor. Then you can apply. So we generally take 5 to 6 years. It took 4 months for him, and he wrote his habilitation thesis. It's a very interesting topic. Contributions to the theory of affinity and valency. A concept of bonding much before atomic structure was perfected. So think of the imagination that how atoms combine to give rise to enduring structures and molecules with unique properties. That certain atoms, they combine with certain atoms, not all atoms, and depending on its valency, that means its attraction power, which is called affinity, it will form a molecule with certain number of other atoms. That's basically the valency. And in this habilitation thesis, he wrote that rigid valence, that means that carbon has 4 doesn't necessarily mean everyone will have the same fixed valence. It may change. And in fact, this habilitation thesis is the foundation of what he was going to discover. So Werner published that work, and then he got a good grade in his habilitation thesis and was appointed as a kind of unsalaried lecturer at Technical High School, at the Selby One. That means you can give lecture now, but you won't get salary for that. That's a good time for thinking big. And that time he was actually working on this coordination chemistry. So as he wrote later on in his Nobel lecture, that during this great era of development of organic chemistry, during which the theory of structure was perfected, the molecular compounds, please note this word, molecular compound. So the molecular compound was the term used by the chemist at that time, what today we call coordination compounds. and they had become state children. And attention will continue to be given to few of them because they were of practical interest. What practical interest? And going to that, as I have already indicated, that when he was doing his military training, he got lectures on indigo, how indigo is synthesized, because he realized that color is becoming an important thing in industry. So organic molecules, they show color. Some inorganic compounds were also prepared by a lot of other chemists which show color, but why they show color and what are their bonding properties were completely unknown. And that is something is called cobalt ammonia compound, which I will touch upon. What are these molecular compounds? From time immemorial, we have been using, human civilization, we have been using this coordination compounds or molecular compounds. Earlier days, people used, plant extract along with for color. So this was one such plant extract that you get from, this is generally you find in the Himalayan region, from madder plant. And the root of the madder plant is, if you just boil it, you get red color. And that red color was actually used as dyeing of clothes. But problem is that these were water soluble. So you take that liquid, extract from the madder plant root, you just dip your white dress, you get colorful red compound, dry it, you use it. Because earlier, before that, if you just look at the sculptures, the paintings of the old Roman Empire and other things, dresses were white, right? Because the color concept was not there. So the color concept started during this period of industrial revolution and other things. Now, what would happen if you have something which is water soluble? You dry it, you get red, very nice red cloth. But then next time, when you wash it, then the color will go. So it was a problem. So what they did, they used to take this madder root extract and mix with a soil, a specific soil, which contains aluminium, because soil contains calcium, aluminium, magnesium, and very different Lewis acidic metal ion. And this Lewis acidic metal ion can combine with this particular unit, three of them will form a tree skillet, and then it becomes a compound which is not water soluble. So then they used it as an additive, the soil additive, and they used it for a long time, but people didn't know that why it shows color, what is the compound and all. And even you know that long back Prussian blue was, color was developed by accident. If I want to talk about Prussian blue, it itself will take one lecture, how it was developed by accident. But many other compounds, colorful compounds were known, but their composition, their structure, how they work, nothing was perfected because there was no theory to explain. But as I said, that in industrial requirement, a lot of colorful compounds were prepared by many different scientists, both in academia and in industry. And such people like Augustus Gain, von Treni, Wilson Gibbs, they worked in industries. So they prepared a series of cobalt and ammonia containing compounds, what all of you study in your undergraduate coordination chemistry textbook. The first example, that if you take a cobalt salt like cobalt chloride and add a different equivalent of ammonia, you get different colors. But why they show different colors? What are their composition? Nothing was known. But since they were useful, they give color, industrial perspective, it was perfectly acceptable. Because, as long as it is useful, get business, that's perfectly fine. You really don't need to get into the molecular structure, understanding of everything about the compound. But there will always be intellectual mind, curious mind, who will try to find out what is that. So a lot of people work, but two important people like Wilhelm Bohnstrand and his students show first your attention. They came up with a hypothesis that this cobalt ammonia compound, when you have 6 ammonia, They say this is more like an organic chain theory concept. That ammonia will bind to cobalt and chlorides which are joined with ammonia, they are not ionized, they are ionizable. Those chlorides which are connected to cobalt, they are not ionizable. But one thing is very clear here, you see, is something that Sophus-Jorgensen could not come out from the hypothesis of rigid valency, that means fixed valency. Because cobalt chloride means valency is 3. And in this chain structure, the 3 valency, they always kept it. And they said that, okay, in this compound, 3 chlorides are ionizable. In this compound, 2 chlorides are ionizable. In this compound, 1 chloride is ionizable. And in his paper, Jorgensen did not talk about this. Rather, very subtle way he said in this paper that this compound may not be isolated. But it was observed the color is different. So, in this hypothesis, they could not come out of these fixed valency things like carbon has 4, cobalt chloride, the valency is 3. But how come you cannot explain the experimental result that 3 chlorides are ionizable? If you add 3 equivalent of silver chloride, silver nitrate, 3 equivalent of silver chloride will precipitate. In this case, 2 equivalent silver chloride will precipitate. In this case, 1 equivalent of silver chloride will precipitate, but they remain silent about this molecule when you have cobalt chloride and 3 equivalent of ammonia. And that, after this, came the Big Bang. In 1893, Alfred Werner published his theoretical framework on the contribution of the constitution of inorganic compounds, and which was published in Zeitschrift für Organische Chemie, which means Journal of Inorganic Chemistry, in 1893. And look at the number of pages of this paper, 33 plus 30, 63 pages paper. And this 63-page paper, he talked about his theory. And what is that? He postulated that a single atoms or molecules could be joined and grouped around a central metal ion to form a metal complex. And again, unlike Jorgensen's fixed valence principle, or in organic perspective, Kekule's directed valence, fixed directed valence, out of that concept, Werner came out and he said that for this type of compounds, there will be 2 types of valencies. One is a primary valency and another is the secondary valency. The primary valency is something called ionizable valency, what we call as the oxidation state of a metal ion in a complex. And the secondary valency is the total number of different atoms or groups that connect to the central metal atom, what we call coordination number. So he said that when you have 6 COCl3 and 6 ammonia will surround the metal center and the chlorides will remain outside. And to keep this number 6 fixed, when you have 5 ammonia, 1 ammonia is less, and therefore the chloride which was outside, which is an ionizable valency, will now come as a secondary valency, and that way the secondary valency must be satisfied, which is 6 in the case of cobalt. When you have 4 ammonia, 2 chloride will come out. When you have 3 ammonia, and there will be 3 chlorides. So if you go, there will be 3 plus, this will be 2 plus, this will be 1 plus, and this will be 0. So this should not show any conductivity. This will show 1:1 ion conductivity, this will show 1:2 ion conductivity, and this will show 1:3 ion conductivity. And what today we write it like the coordination sphere, 3Cl3, this is ionizable valency, and this is primary valency. And he could explain the experimental result obtained by Jorgensen and others. He also postulated that what would be the geometry of this directed valency. When you have 6 groups around a metal center, then he said that if the geometry will be octahedral. There are many possibilities, right? You can arrange 6 groups around one metal center. It could be hexagonal planar, it could be trigonal prismatic, it could be other geometry, but depending on the experimental results, that how many isomers in which case is possible, this way we came up that no, the geometry will be octahedral. That means 6 groups will occupy the 3-dimensional space to give rise to a geometry which is octahedral in nature. And why he came up with this, I will tell you right now that if you remove one, and then if you put a different groups like, let's say A5B, that would also be a distorted octahedral geometry or octahedral geometry. But how many isomers are possible here? 1, right? Any place you keep the red, because it's a symmetric structure, it is basically the same. So therefore, only 1 isomer is possible. But the experimental results that he relied on, and that experiment was actually done by Jorgensen, that if you have MA4B2 type of system like this, then 2 B's you can put adjacent to each other, or you can put just opposite to each other. So that means you get both cis and trans isomers. So 2 isomers are possible. And precisely this result was there. This result, experimental result, was obtained by Jorgensen. But since Jorgensen followed the classical concept of fixed valency, he could not utilize his experimental result. And they had to wait Alfred Warner to explain, and he only took the experimental result of Jorgensen and explained that what could be the geometry. If you have 3, MA3B3, then MA3B3, there will be also 2 isomers, right? If you can consider this one is the north pole, this one is the south pole, this is equator, right? So going from north to south via equator, and therefore this is something called equatorial isomer, right? Or you can call it, meridional isomer. So this is like along the meridian, from north pole to south pole along the meridian. There is another possibility. Look at the octahedron. If I just held the octahedron like this to you, in front you have a triangle, right? And towards me there is another triangle, but 2 triangles are not eclipsed. They are like moved one from another one like a star, correct? So this is not octahedral, that's why called, trigonal antiprism. If you have a trigonal prism, one triangle will cover the other triangle. If you look from the triangular face. So you have an equatorial, you have a meridional isomer, or you can have a facial isomer like this. So you see that the reds, 3 reds are there in one face, which is the one in front of you, and 3 greens are there in the face towards me. And you can see that this is an antiprism. So based on that, we came up with this. Please stop me.
Please
Well,
5 minutes.
Okay. Otherwise, I can keep on going. So, all right. So facial and meridional. This group also isolated the platinum ammonia compounds, where platinum plus 2 oxidation state, and they say that there are 2 isomers are possible for PTNH3 whole 2 Cl2. And this can only be explained if you consider the primary valency and secondary valency. Cis and trans, and you know that cisplatin, this is a very known compound which is nowadays used as an anti-cancer drug. Okay. I'll end soon. So by this time he becomes very famous, because even his rivals also accepted his theory, because there will always be rival. I don't want to get into this rivalry story. But then first time he is now entering to a university. As a student, he was never allowed to go to university because he never studied in high school. Very regimented education system, right? But as a faculty, as an associate professor, he is now entering the University of Zurich. But the problem is that since he worked with an organic chemist, he could develop a big, a revolutionary theory which is related to molecular compounds, inorganic compounds, but he was not allowed to teach inorganic chemistry because of internal rivalry, why he was given a position. That thing happens everywhere, every time, as long as human are there. So, after that, he started his experimental work because now he got a lab in Zurich University. And his group made use of traditional tools because there was no technology that time, right? Sophisticated instruments were not there. Only that traditional tools like colors, melting points, solubility, sometimes conductivity measurement, polarimetric studies, only those were the available tools. And using those tools, Warner and his group, over the next 25 years at the University of Zurich, prepared about 8,000 compounds. And almost half of these compounds are still there in the Zurich University Museum. I will show you one example and then, but one important thing that many of you probably do not know, and I was surprised when there was an international year of a periodic table a few years ago, Alfred Warner was never acknowledged. But if you look at this paper in 1905, he published in Berichte, it's a German science magazine, where he in fact designed a periodic table, and he said about many of the properties of the periodicity that his previous successors, predecessors on that area, they never ever talked about. Okay, then he first published his experimental paper after that theoretical framework that he developed. In 1893, he published an experimental paper on platinum-4 compounds and their conductivity data and what would be the structure and everything that he published. That was the first experimental work on his own theory. Because there was a reason. Because Jorgensen wrote a paper in 1894, Jorgensen missed his paper, experimental paper. Then Jorgensen in his paper, because they are scientists, right? I mean, when you have some idea, I differ with that idea, we do not fight with swords. We fight always with pen and paper. And so, Jorgensen wrote in this paper that one who proves too much proves nothing. And the important thing what he wrote, that a criticism of Barnard's system was not the purpose of this work, that all the objections to his own theory of the ammonia metal compounds, which even, note the word, such a skillful theoreticians like Warner had put forward are not correct. That intellectual speculations are not sufficient to construct a barrier theory for the ionic metal ammonia compounds. Only unbiased experiments will be able to resolve the complicated identity of this extensive group of compounds. He already published one experimental work, subsequently he published another experimental work, where now he took a compound prepared by Jorgensen. And that's basically this ethylene diamine X2 compound. So it's a bidentate ligand, you all know, that gives rise to two isomers, right? Cis and trans. And the trans isomer, because you have a plane of symmetry, it doesn't give any optical activity. But when you have a cis isomer that has a chiral axis, and because of that, it gives rise to optical activity. And that was he published in this paper in 1895, and then finally he became a full professor. But there was a problem with his professorship because he was not a born Swiss. So how do you become a professor? The easy way, that you find a girl from Switzerland, marry her, and then you can become a Swiss citizen, and then you become a professor. And in fact, in this case, what we call Bangla, Bhatkalir Kastari, his professor did actually. And these are all documented, I'm not telling you. Okay, so this is what he did. So in this paper, he said that it's a bis-ethylene diamine, 2A can be cis to each other, or 2A could be trans to each other. But the cis will give rise to optical isomerism. And that is also true for when you have another bidentate, which is called triskelate, that is also optical activity. By this time, he became very famous. Alfred Werner supervised almost 230 doctoral dissertations, but only 46 students were from Switzerland. The rest came from different parts of the world, signifies how important this research group was there. Okay, and this is actually the two different isomers that he isolated. And you see that his students here actually wrote the level at that time in around 1911 that he isolated the cis isomer, the lambda and delta, two enantiomers using a chiral anion, which is the 3-bromoate camphor sulfonate, and they isolated pure enantiomers by making diastereomers and changing their properties. And in fact, another compound that was taken from his archives later on, about in 2011, after almost 100 years, there was some problem with this compound. What he indicated in his paper that there is an inherent problem with this compound, that we do not get 100% pure enantiomers, which later on, with the development of new technology, what we call twin crystals in crystallography, later on in 2011, the head of the department of the chemistry department of Zurich University, they could solve the riddle what Alfred Werner anticipated 100 years ago. Chris Gillet's shows right too, but the problem was, I'll just finish. So the problem was that although people accepted his theory, not everybody was accepting it, because the idea was, see, ethylene diamine, you have carbon there, right? Any ligands where he used, all were organic ligands. So organic chemists, a part of organic chemists who were rivals, they were saying, this optical activity in coordination compound is actually coming because the ligand what he is using contains carbon. So he was determined that he will make a optically pure chiral compound without any carbon. And when he presented his paper in 1911 in Swiss Chemical Society meeting, which was attended by a lot of dignitaries from all over there around the world, he presented a paper that the compound called Hexol, which was a pure inorganic carbon-free chiral compound, which his research group could isolate both the enantiomers like delta and lambda. And here you see this central atom is coordinated by an inorganic ligand. This is a bidentate ligand, this is another bidentate ligand, this is another bidentate ligand. No carbon. A metal complex acts as a ligand to the central core. And again, in 2011, the research group of Helmut Berke, the head of the department of Zurich University, they took the crystal from the archive of the samples prepared by Alfred Werner students and saw they were 100% optically pure for both the enantiomers. Anyway, finally, in his lifetime, about 1890 to 1919, he's published 174 research papers, but 230 doctoral theses he supervised. Okay, he was not a born Swiss, but he was the person who founded the Swiss Chemical Society. He wrote books, first one on stereochemistry, and later on he wrote a book on new idea in inorganic chemistry, which was actually used in Germany for almost 100 years, even after his death. Okay, since 1906, he got several nominations, but every time the problem was that whoever were nominating him, they were attaching Jorgensen along with him. If you ask me, I would say it's perfect because his work was based on experimental work of Jorgensen. Jorgensen could not explain. So the first one, it was given to Jorgensen several times, but later on, since post 1911, he only got nominations, and overall he got 19 nominations in about 7 years. But only his group proved the chirality of coordination compound, which means without any carbon containing compound, and his theory was finally accepted and he was awarded Nobel Prize in 1913, along with Rabindranath Tagore, who got Nobel Prize in the same year. So he had a lot of health issues that time. He applied for, after Nobel Prize, he applied for leave, but you know, a Nobel laureate want to leave a department, government doesn't want that. So he was writing, government was not responding. So at one time he was so frustrated that he left the university because citing health issue on October 15, but just 1 month after leaving the department, on November 15, 1919, he died. And that time his age was just 53 years. Unbelievable. Now to end, that what he anticipated, that this new area would open much promising prospects for the treatment of new fields of inorganic chemistry. And indeed, over the last 100 years, more than 100 years, this has opened up a lot of new areas. Talk about organometallic chemistry, analytical chemistry, bioinorganic chemistry, supramolecular chemistry, catalysis, geochemistry, mineralogy, material science, many more, and many more areas are coming up. They are all fundamentally based on this principle, and without this, we, inorganic chemists, or inorganic chemists, or allied area, just cannot survive. This signifies the implications of his research, his findings, and his contribution to science, which made him one of the father of inorganic chemistry. I will end by quoting Leopold Werner that Alfred Werner was a star of unequaled brilliance in Europe's intellectual firmament. Coming from a humble background, this hero in mind attained the lifespan of 50 years of brilliance, which will continue to shine for centuries. Alfred Werner passed away physically, but making full use of his ideas will be a task for generations. And obviously, it's not we, the future generation like you, will take it to the next level. Thank you very much.
So I think all of us agree that this was a kind of a wonderful lecture. I mean, to understand the beginning of coordination chemistry. So that forms the basis of everything else, right? Whether you study organometallic chemistry, analytical chemistry, whether you are poisoning by lead poisoning or mercury poisoning. So you always use chelating groups. So I mean, coordination chemistry is something it was probably known, known in nature. Yeah. It was rediscovered by mankind. It was also a kind of a great discovery of mankind, the ability to know things. I mean,
say talk about hemoglobin, right? It's also a coordination compound. As long as we are here on this planet or any other animal, they all have this coordination compound. Be it in living organism, be it in nature or any other place, this was there. But finding it out, coming up and placing it in a proper format is something that only revolutionary scientists can do. Obviously, everything is there around us. Only great people can see.
So, thank you very much. I think we will have one more lecture, and Professor Paine would be around. And Professor Paine would also be visiting your college, right? So, I think we will have more time to discuss with him. So, now I request Professor Singh to come and talk to you about physical chemistry and spectroscopy. And he has put his title as seeing molecules with light. How do you get to see molecules? Thank you.
Yeah, it took so much time.
Okay, I know most of you will be hungry, right? I'm looking for their lunches. So I will try to be very precise and very fast. Try to finish the things within 15 or 20 minutes. Okay. So you have heard two talks, one talk by our director where he explained beautiful history of our own institute, and then Tapan explained you nice, complete biography of Professor Warner. So I'm not going to talk about particular scientists or anything. I'm going to talk which we see every day. So it's basically light, which we see every day. We realize their importance in every day, but lots of things are still undiscovered. Okay, so this water has water molecule. I'm helping you out. I'm not asking what it has. It has water molecule, right? We all know that it has water molecule, but we cannot see them from the eyes. You will say that we cannot see them by eyes because it's a transparent, right? But we can use the different light sources to characterize them. Now, if you look this water bottle, water is very static, but in real world, this water is not at all static. Okay, so there are several such examples where things happen. We see the macroscopically in bigger picture, but if we try to see microscopically inside of it, we cannot see. But light is such a beautiful thing which can help to see inside of that, not only inside of that, but also try to understand that whether the process is static or dynamic. And if it is dynamic, then what time scale? Okay, so let's start with light. I'm very sure you all have been taught about light, right? You all are BSc students, or someone is probably some master students. So you know that light has been told that electromagnetic radiation, right? Different wavelengths, different properties. So if I go radio waves, microwaves, infrared, visible, UV, X-rays and gamma rays. So if we go from this region to this region, you will see that the wavelength is decreasing. And all these lights are available in the nature, basically. We see them every day in this or that forms. So like examples are given here. If you look the radio wave, we use transistor, FM. Sab sunta hoga FM, right? So that is the radio wave. Microwaves, our director talks about we use microwave for heat source. So we use microwave. Actually what we do in the microwave, how the things get heated, you know that? We rotationally excite the water molecules, and that creates the heat. That helps basically heating the things in the microwave. Infrared, everyone uses at home, TV, opening the TV set and other things. Visible light, most evident example of light which we think it is light basically. UV comes from the source. We use glasses to cut the UV. X-rays we use in the medical field that our director introduced. We can see the bones and everything using that, and gamma rays used for the nuclear reactions. Okay, so these are the different examples already available in the nature in different forms. As I said that wavelength is increasing, a wavelength is decreasing. So if we talk about the energy is decreasing. In all these light sources, as I talk right now, the most important is visible light. You know why? जो दिखता है वो दिखता है. So visible light you can see from your eyes. दिखता है इसलिए दिखता है. But all other light sources are equally important, although we cannot see them. But visible light is important. We have been taught with this VIBGYOR like things. So wavelength, you can see that changes from 380 to 750 nanometer. So these are the visible light with your eyes responses. So now if I want to see the anything, I will have to use the visible light, right? Because that's what our eyes responses. So let's say that what our eyes can see from the visible light depends on the size of the system. Okay, so the wavelength, as I talked about, 340, 380 to 750 nanometer roughly. So what we can see soccer ball. It's big enough from our resolution. We can see them. We can see the small grain of sands, still good enough for our resolution. But if we go to bacteria, we cannot see. We cannot see even if we use the visible light. Bacteria is kept here. We cannot see because our spatial resolution of eyes are gone. Now, what scientists did, they made bigger eyes in form of microscope. So what we did, they uses lenses and other thing, focus it so that we can see things which cannot be seen from our eyes. बहुत सीधा भाषा में अगर बोले तो आँख को बड़ा कर दिया, ठीक है? They have made eyes bigger. So now there is also limitation. So limitation is that yes, you can see certain wavelengths, certain objects till certain size. If it is within the diffraction limit of the microscope, you can see those images. So you can see bacteria and virus very easily using this microscope. Image will look very clean. But if your system is even smaller than that, you cannot see the things. Okay? For example, if you want to see the protein, DNA and molecule, you cannot see. Even if you use the microscope. Scientists with bigger eyes also, you cannot directly see by the light because they have the diffraction limit. Even if you use 532 nanometer, diffraction limit is 200 nanometer. So the maximum size which you can see is that 200 nanometer. And these all things are smaller than that. So you cannot see directly by the light. So the problem is the size mismatch. Resolution issues arise. Now how can you see them using this light? So here comes in the picture. Picture is that the class में जितनी लड़का होता है तो बात नहीं सुनता, right? Then you are very stubborn. You do not listen the things. So I hope you guys are teachers, right? Okay. So what your teachers do? They create perturbation in you. They force you to listen that. And that's what light can do here. And if you can use this perturbation, you can see things happening beautifully, not only by the visible light, but all other sources which I talked right now. Okay? So I will just talk few examples how it helps, not scientifically, but also in practical life which we are seeing every day. Okay? So we can use light source can be anything, what I talked in my past slides, from the radio to gamma rays, anything it can be. You shine on the light, light will not light it. Why light will not light it? Because molecule is basically stable. Like you are stable in one place. If someone force you, someone give you excess energy, you will not like it. So what you are doing by photons or light sources, you are exciting this molecule, disturbing its stable state, and it will not like it. But what will happen that when you give to light to this molecule, the states are perturbed. States are perturbed means if molecule is resting and you give the light, it will get excited. The electrons will get excited and go to the different states. Now it will depend what light source you are giving. Now, if I am stable state, if I am like I want to be in this state, if someone asks me, give me energy, if I go somewhere here, I will not like to be here. I will like to come back to this place. And when this light interact with this molecule, they take them to some different energy states. And now this this energy, the molecule, what it will try to come back to its original state in different ways, different mechanism, different possibilities, different environment, different molecules properties. These all things will control this process. So we can visualize these effects and we can characterize the molecular property by this process. So what will happen? You put light, molecule will get perturbed, energetically perturbed, and will go to different energy states. Then there will be certain response of the molecule, which I was saying. It will try to come back in its original position by showing the responses. Now you can measure those responses, which is called spectrum, some cases signals, some cases images, many different ways. So these spectrum, signals or images will provide you different molecular properties, which probably you would have not seen if from the bare eyes or from the visible light. Okay, so since I am saying that if you put the light, energy of the molecules get disturbed, so we must know that what energy state a molecule may have. Okay, so these are the energy diagram of the molecules. So we just heard that the ground electronic state, right? Electronic state. If this is excited electronic state, the ground electronic state may have several vibrational states, and each vibrational states may have several rotational states. So if we talk about energetically, the spacing between the electronic state is very high, followed by the vibrational state, followed by the rotational state. Now, since these spacing are different, so if you want to use the light to go to the different energy spaces, your responses will change, your excitation will change, and for the response because of that excitation will be changed. So for example, if I want to go to S0 to S1, the transition will come in the UV visible region. You must have been taught you use UV visible spectroscopy for different purposes. You can use the light to excite the molecule in the vibrational state. So 0 to 1 transition, so when electrons goes from 0 to 1, so you can probe the vibrations of the molecules. But this is not in the UV visible region, infrared region. So now this process you could not have seen from your eyes, because eyes are only selected for the visible range. Okay, the electrons can rotate in that region also, and that will appear in J0, J1, J2, J3. So here things will appear in the microwave region. So you can see that when the spacing of the states are changing, we give the light of different, according to that spaces, means resonance conditions, the outcome of the responses will be in different regions. So we can probe all these regions to see the effect of the light molecule, which could have not been possible what I was talking earlier. Okay, so let's talk about these two examples, electronic states and vibrational states. I will focus only these two examples, how these things happen and what we can do using them. Okay, so let's say this is electronic transitions. So molecules are generally in S0, mu0 state. When you excite them, excite means you put the UV visible light, it will go from this S0 to S1 state, may go from 1 to 2 state, different transitions are possible. I have represented like a spectroscopist, but this is simply homo-lumo transitions. Okay, you must have heard or you have been taught about the sigma to sigma star transition, pi to pi transition, pi star transition, n to sigma star, and then to pi star transition. These are all transitions of these electronic transitions which I am talking right now. Okay, but it's not like that you put the light process will happen. There is a check fact that there are conditions in which this transitions will happen, and that is called selection rules. For any transitions to happen, the states which I talked, there is always selection rules which allow them. If your system follows that, then only these transitions are allowed. So, like for this electronic transition, your selection rule says that spin should not change. It means singlet to singlet transitions or triplet to triplet transitions should be, and there should be some change in the angular momentum during this process. Okay, so I will not go much detail about that. So, what we can do from that and how it is done. So, how we do that, we use, as I said, that these are the UV visible transitions. You take a source, UV visible source, monochromator, you use particular wavelength, then put it into some sample which you want to understand. There will be detector, because now you cannot use eyes. Eyes will not be sensitive to that. You need a detector which will work as eyes for you. And you can measure the spectrum, which I said that response, different responses. Now this is the spectrum. You can see that this absorption spectrum comes from the 200 to roughly 500 regions, which is UV to visible region range. Okay, what we can do from this? What we can do this using these things? So the first and most important thing from this absorption spectra, we can do that. We can know the concentration of any sample, unknown sample, right? By using the Lambert-Beer's law, right? So let's say if you have to make some solution, you have two ways. You can weigh them, you can get the volume, and then make the particular concentration of the solution. But this is not always feasible or not possible. If let's say that you have to make picomolar concentration of some very costly samples which you cannot weigh, then how will you make it? So the best thing is that you make some random solution, measure the UV visible spectrum, and from that you can apply the Lambert-Beer's law. You know the absorption and you know the path length. From there you can calculate the concentration of the solution. Now it can be used to identify that what kind of transitions are that, like which I said that pi to pi star, n to pi star, sigma to sigma star. For all these transitions, the wavelength is in the different regions. So you can identify it's very useful for the biomolecules like proteins and DNA. They have the characteristic band in the 260 nanometer. So you can use them and you can understand the nature of these molecules. Okay, so this was the absorption spectrum. But the molecules will not be always in the excited state. If you excite them, molecule will not reside them at that state. They will try to come back to its original state. Let's say, अगर आपको घर में कोई डांटता है, so डांटने पे क्या होता है? आपको भी रिवर्स में गुस्सा आता है, right? Everyone gets annoyed. But that annoying nature you don't keep for quite long. What happened? After some time, you also get cooled down. And that exactly happened here. So if you excite the molecule, this was what I was talking, S0 to S1 transitions. After that, the molecule was excited into some state which he does not like, because molecule love to be in the ground state. Molecule does not like to go to excited state. So what it does, it tries to relax back to its ground state. So it relaxes back by two different processes. One way, it can give back light, right? So here, which is called fluorescence. So what is happening? Molecule is coming from S1 to S0 state by giving back to the light. This is what the fluorescence process is that. And it's not that always molecule will come back to the ground state by light. It may come back without giving light. So that is called non-radiative process. So there are two processes by which molecule can relax to the ground state. One is that by giving the light, that is called fluorescence, and other is that without giving the light, it is called non-radiative decay. So fluorescence is basically radiative decay, non-fluorescence is basically non-radiative decay process. Now, the balance of these two processes will tell that how much bright molecule will appear to us, which we see in daily life, and probably you have not realized them. Okay, so if we measure, let's say that for example, I have put a Jobson spectrum here of a molecule, and this is fluorescence. You can see that fluorescence is at longer wavelength than this. Basically, it's a red shifted to that. Why? Because molecule is, you have excited here, then it relaxes back, and fluorescence is appearing in these states. So energy is always less than what you have excited. That's why this emission spectrum is always shifted compared to a Jobson spectrum, and this is called Stokes shift. And this Stokes shift always happens. The amount of Stokes shift will tell you that how much molecules are being stabilized in the excited state, and that will depend what kind of environment molecule is facing. Okay, so this Stokes shift was observation and observed by a scientist called Stokes. Basically, on his name, this shift is known as Stokes shift. Okay, let's talk some example, some scientific example first. So this is a molecule. Okay, now if you put this molecule in different solvents, you can see then that their color are changing. Not only color are changing, but their intensity is also changing. Color intensity is changing. So this is what you will observe from your eyes, and this is the spectrum of all these things. So you can see that from the non-polar to polar region, if you go, molecules shows huge shift according to the polarity of the solvents. So imagine this molecule, which you would have not seen, but if you measure the fluorescence, you can clearly see that what color this is showing, how this color are changing with respect to the solvents, and how these solvents stabilizing these excited states. So this is the beautiful phenomena by which you can see the electronic state of any system, any molecule. Okay, this was the scientific example. Probably you will not like it. So I am showing you something which you see every day. Okay. What fluorescence can do. Okay, so the first example is cancer cell detection. Okay, so when there are some biological irregularities happen, then the cell become polluted, and it's called cancer cell. And this disease is quite spreading quite fast. The biggest problem is detection. Not only detection, but also treat them perfectly in guided manner. Because let's say that you have a cancer cell here, right? But if around them, all of them are good cell. If you kill good cell by some medicines, then it will kill cancer cell as well as good cell. But that's not good for you. Your whole immune system will be killed, and you will not be able to survive outside. If any part of reason after outside you cannot face. So this was the biggest problem. How can you do the guided operations for the cancerous cell? So this is the normal tissue. If you see from the visible light are in general source, you cannot detect them clearly. But if you see the cans use the fluorescein molecule, the molecule name is fluorescein. If you seed them in our system, where in tissues which you want to see, where there is a possibility of the cancer, and then see their fluorescence, you can see these things are extremely bright. and the picture become very clear when you are doing the operations. So this is whole tissue. Out of this, only this cancerous tissue is there. Okay. Now, if you use fluorescein molecule and target them, then you can clearly see that, doctors can clearly see that you have to remove only this part, not the whole tissue. So this fluorescent technique is very useful in this manner. So you can do the targeted operations using a fluorescent dye molecule, seed them, and you can see them. Now you can see the blood vessel. You cannot see the blood flow, blood vessels by your eyes, but you can use the molecule called ICG, indocyanine green. So what we do, you need to flow them in your vein system, and then you excite with the NIR things, your vein will look like this. You can see the X-ray clips clearly, all the veins. Okay, so this is the other example of the your fluorescence. Okay, the biggest thing is this. You have heard about the heart blockade, right? How to detect it? Your heart connects with the 3 arteries. Okay, the arteries, blood, it takes arteries. Basically, blood goes through these arteries to your heart and then pump out. Pump in, pump out process goes in. Carries on all this. Now, what happened that हमें तो बहुत स्ट्रीट फूड खाने का शौक है, खाते रहते हैं, तो all cholesterol goes there and stuck there. And then after that, arteries wall become thick, no blood circulation. After certain time, there will be no blood circulation, and one day you will have a cardiac arrest. So the question is that how was to detect them? So people used to detect it by X-ray initially, but the resolution was very bad. It was not very clean. Then people realized that why not to use the fluorescence of certain molecules which can make them visible very clearly. And this dye is generally being used right now, that ICG dyes. You flow them, you excite them, and you can see all the arteries and associated veins from that. Now, so you can see this image here. The artery is blocked. Okay, this is narrow artery. The blood flow in these places are not very clear. You could not have seen it from the X-ray or using other things, but the fluorescence of this molecule make it very clear. Now, you put the stent, which is called angioplasty. You have put the stent there, and you can see all these things very clear. These arteries, these supporting veins are very clearly being seen. So this is the advantage of the fluorescence spectroscopy. You can have the right kind of the dye, and you can see all these processes which could have not been realized. And this is, by the way, being done online. Online means patient is there, the process is being done, and you can see all these things on the screen happening with time. Okay, so this was the beautiful invention was done by these things. Okay, let's talk some scientific stuff on DNA. If we have to see the DNA molecule, it's transparent. You cannot see them. Okay, so how to see the DNA molecule? So lots of dye molecule was synthesized. You must have heard DAPI, ETBR, all these things. You make the solution of that. It goes and binds to the minor group of this DNA, and you shine the light. You can see the blue or green fluorescence, which basically dictate the DNA things. So you can see that DNAs are being visualized. If you see from the bare eyes, the first thing is small size. Even if you use a microscope, you cannot see them. But if you use the dye molecules, you can clearly see them. So this is how the people in the lab basically characterize this DNA molecule using the fluorescence, and not only characterize, do lots of other things for disease-related research. Now, this is the detergents which we do. We do every day at your home. If you want to put some color in your clothes, you use the detergent with the fluorescent molecules, and then you will get the color. So this is white, no fluorescent element. If you this blue color, you can find that your cloth have become blue. So this is the huge range of the applications of this fluorescence technique in your daily life. Not only daily life, but for research in this white LED bulb which you use, which gives we see the fluorescence spectrum in the broad region for our things. Currency note, we check in the UV light whether your note is correct or not. So it's a huge range of applications. I am not written everything, few of the popular applications. So basically, the fluorescence spectroscopy let you realize that those things, those phenomena, those processes which you could not have seen from your naked eyes. So this is one example where I talk one technique where light can force you to see many things. Okay, so now next I will go to quickly. I will go to other thing which I was saying that this was the electronic state. Now the molecules can vibrate also, right? So molecules, the two ends of molecules are associated with bond, which you can treat like a spring. Okay, so a spring have certain motions. You can stretch them symmetrically. You can bend them. Okay, so based on that, how you do the process, you pull them symmetrically, pull them asymmetrically, bend them. The frequency of those things will be different. Okay, so if you see that the frequency is basically root over k by mu. So k is basically force constant. Force constant means how the spring responds to the perturbations. Okay, and mu is a reduced mass. So let's say for a given molecular system, if you want to bend something and stretch something, so bending is always easier rather than stretching the things. So bending force constant will be less, so the frequency will be less. So always bending frequency is less than stretching basically. But if you take different molecules, then your reduced mass will come into the picture. So these vibrations basically play an important role. Now how to do these things? You will have to, earlier case we were using the UV visible light to excite the molecules. But here, since we are looking the vibrations, we cannot use UV visible light. So here what we use the IR light, because your energy gap was correspondent to the IR. Okay, so here we can use IR light, excite the molecule, and then we can see the emission of the IR light. Okay, again I said that earlier for the UV visible spectroscopy that there are certain rules which if you follow, then only the transitions will happen. So in the vibration case also, there are certain rules which if you follow, then only things will happen. So this was the the rule is that your dipole moment should change. Okay, during the process. So let's say you are stretching the things, then dipole moment should change. For example, let's say HCl molecule, two different atoms are connected, you stretch them, during the vibrations, dipole will change. But if you take this Cl2, there will be no change in the dipole during the stretch. So it will not show IR spectra, but this will show. For same molecule, let's talk about the asymmetric stretch of the CO2. Asymmetric means you pull it this way, but that will not go in the same distance. So in this case, dipole moment will change more compared to this guy. Here there will be no dipole moment change for symmetric stretch. So that's why the dipole moment change in the symmetric stretch is 0. Okay, and for asymmetric change, there is a certain dipole moment change. So you can see the IR spectra of this molecule, you cannot see the IR spectra of this molecule. Similarly, for bending, the dipole moment will change. But if you take the CH4 molecules, there will be no change in the dipole moment during any vibration, rotation, anything. So you cannot see the vibration spectra of these molecules. So the thumb rule is that your dipole moments should change during the motions. Okay, and what we generally do using this spectroscopy is that we can characterize all different modes which we could have not done. So like OH alcohol, OH carboxylic group, acid NHME, CH these all groups can be characterized by using this principle because the force constant is different for all these different groups. Reduced mass is different. So based on that, their signal will come in different regions. For OH, it will come to 3200 to 3600. For carboxylic group OH, it will come 2500 to 3300. For Me, it will come 3300 to 3500. For alkane, it will come to this region. So, depending on what group you are looking, what is the force constant, based on that, your stretching frequencies will keep on changing. So, you can characterize all the functional groups using this vibrational spectroscopy. Okay. So, let's come to the basic question which we discussed first. That how was the water molecule inside that? That was the question which I started. We could not have characterized these things because it's a transparent, it has no response for the visible light. But you can characterize them using IR spectroscopy, which I talked right now. How you can characterize them? So the chemical structure of the water is H2O, right? But can you measure the H2O spectra as H2O? Means only one water molecules. Okay. So because how many water molecules are there? You don't know. Millions, billion, trillions, any number is small. So this is so many water molecules. But if you really want to understand water spectrum, you have to measure one water spectra. How will you measure one water spectra? You will have to get only one water molecules, right? How can you do that? Only one water molecule. You can do it if you can keep it in isolation condition. Isolation means it is in the solution. But if you can keep that water molecule somehow in the vacuum thing, then you can measure only one water molecule. Not only one. You can sequentially see that 1 water, 2 water, 3 water, 4 water, how they form their structures. So that is called supersonic jet cooling. I am not going to talk about that. Just in that case, there is a very high vacuum will be there. So and there will be very good control where you can see only one water molecule. And you look the OH spectra of that molecule. So we are looking OH stretching. So what we can see that asymmetric stretch appear around 3730 and symmetric stretch appear around 3650, right? So you know, if you want to pull something asymmetrically, then frequency will be higher. If you want to pull them symmetrically, frequency will be lower. So that's how the water molecule look like. Let's go to our interest. This was the water molecule. And if you measure the water IR spectra, this was only one water molecule. But this is the water molecule with in this solution. So this water molecule spectrum looks very broad, okay, covering from 3000 to 4000 centimeter inverse. We cannot see even this band, although water is there. But one water is look like this way, but the whole water collection looks like this way. And it is not only this. If you look, the band position is around 3400 roughly, 3450, which is 200 centimeter inverse red shifted compared to the only water molecule. So this is different from the one water molecule. What does it mean? How it can be understood? It can be understood by this way. So when you are in the isolation condition, the water is basically like this only, doing this motion, asymmetric, and this motion, symmetric. But now water is not in the isolation condition. Okay? Water, as I said, I don't know how many water molecules. So each water molecules form hydrogen bond with each water molecules. And the distribution, so when hydrogen bond appears, based on the strength of the hydrogen bond, spectrum gets redshifted. Okay? So now you can see that, for example, here you see the water molecule 2 hydrogen, this hydrogen, this OH group is interacting with the oxygen of that, and that oxygen is interacting with the 2 hydrogen of other molecules. So there are various possibilities. One, there could be one water interacting with 1 hydrogen bond, 2 hydrogen bond, 3 hydrogen bond. In many different ways, water can basically interact with these water molecules. So it's a very complex assembly of the hydrogen bond network, very inhomogeneous assembly of the hydrogen bond network, which appears from this spectrum. So it's not visible, you cannot see them, but if you use the IR spectroscopy, you can characterize that how the things are inside of that. Now the next question, which I am not going to talk right now, but what, the water molecule is static here? No. It do very rapid motion. So it's like this way. It's changing very rapidly, extremely rapidly. Not only changing, it's basically rotating also. So it's doing all kind of motion inside of that. But why we cannot see? Why we cannot see that things? Because our eyes can see the things first. Visible light only can see the things which, if it is happening in the seconds. But this process happens in much faster than seconds. So these are very dynamic process which happens in the femtosecond time scale. We cannot see from them from through eyes. But if we use light and advanced techniques, we can decode each and every hydrogen bonding pattern of these water molecules. Okay, and this water molecule behave differently from the other solvents. You must have read density, the dielectric constant, all other properties of these water molecules are different from the other solvents because of this hydrogen bonding network. So basically, these all complex problems which I talked with you could have been resolved using the IR and UV visible spectroscopy. So I'm just summarizing that what IR spectroscopy can be used in various applications. I'm not going to read out it, but numerous applications it has in the real life. So finally, what I have tried to convince you that you can use the light to uncover the molecules which you could have not seen from your own eyes. But if you can use the light matter interactions or light molecule interactions, you can see, not only characterize them, you can use for our real life problems, and you can see their dynamics and other properties also. Okay, so that's it. Thank you. What next? Okay, so he is going to tell you what to do next.